Yay, spinning!
Dude, this is so boring.
Why is it still spinning? The top, one of childhood's most fascinating toys. It's been spinning since 3500 BC. But has anyone stopped to realize the physics behind it?
There are actually many complex physics ideas behind the simple spinning of a top.
Such as a top's axes, precession and the effect of gravity, friction, and angular velocity and angular momentum.
We'll start by explaining the axes of a spinning top. First off, there's the axis around which the top moves on the surface. So the top could be spinning like this, and there's the center of the axis on the surface. Second is the axis when the top tilts, which is known as precession. So as it's spinning, it tilts off of its axis, which leads to gravity and its effect on the top, which we'll explain later. But most importantly, and naturally, the most important axis on the spinning top is the one that goes straight down through the top.
On a perfect top, the third axis that we talked about would go straight through the center of gravity and hopefully would be perpendicular to the horizontal that the top is spinning on. However, since it is almost impossible to create a perfect top, most tops end up spinning off of this axis due to precession and the effects of gravity.
The ever-increasing tilt of the top off of the center axis is known as precession, which is demonstrated here.
As we just saw, as the angle of precession increases, gravity has a greater visible effect on the top, causing it to fall.
Also displayed by this last clip is the idea of the inverse relationship between the angle of precession and the angular speed of the top. This means that as the angular speed of the top decreases, or as the top gets slower, the angle of precession increases and the tilt increases.
A top slows down due to friction between its point and its point of contact with the ground. On a surface with very low friction like this granite, the top can spin for quite some time.
But if we were to put the top on a surface with more friction, such as my hand, the top wouldn't spin for nearly as long. Ideally, if we had a perfectly balanced top and a completely frictionless surface, the top would indeed spin forever.
Angular velocity, as we learned in our circular motion unit, is the speed at which the outermost part of an object spins.
Angular velocity leads into our next idea, which is angular momentum. Just like linear momentum, as we learned in class, which is P equals the mass times the velocity of an object, angular momentum is basically the same equation, just with some different variables. It is the angular momentum, L, equals the moment of inertia, I, times the angular velocity, which Aaron just explained, W. An object's moment of inertia, I, is the measure of an object's resistance to change in its rotation.
Angular momentum L increases as either the moment of inertia, I, increases, or the angular velocity, W, increases. Another concept that goes along with angular momentum is the concept of the conservation of angular momentum. The definition for the conservation of angular momentum is if no unbalanced external torque or spinning force acts on a rotating system, the angular momentum of the system is constant.
These next two video clips show the conservation of angular momentum. The man in this clip will cause the wheel to spin. Once the wheel is spinning, the upward direction of the wheel and its momentum will help it fight gravity, making it seemingly levitate. The horizontal component of the momentum causes the wheel to spin in a forward direction.
The concepts in this video clip are very similar to the concepts in the last video, except in this video the angular momentum pushes the man in a circle on the stool.